Now, diffraction grating, this one is mostly used for light only. All right. Diffraction grating is not two source interference. Okay. Actually, is multiple source interference. The interference that you've learned so far before is all from two sources only. But when it comes to diffraction grating, you're also talking about the interference formed by them, but this time the source is not limited to only two sources. It actually comes from many different sources. All right. So what we'll say here is this. If you remember that under double slit, I'm just going to draw it here. Under the double slit experiment, you had a slit, you had two slits, a double slit. You shine light through the double slit, and then on a screen that you place far off behind, you're going to get a pattern of bright and dark fringes, or a pattern of maxima and minima. Okay, so this is what you see. And then the equation you use was lambda equals to ax divided by d, where we tell you that this one is a, and then this one is d, and then this one is actually x. Okay, now when it comes to double slit interference pattern, you're also going to be doing something similar to double slit, where you shine light through something, but instead of using a double slit like what you're doing here, you replace it with diffraction grating. So a diffraction grating is actually similar to a double slit, just that it has many more slits than just two. So double slit would just be something that looks like this with two slits, but diffraction grating has many slits. All right. So right now for diffraction grating, you will shine light through a diffraction grating. You will also place a screen behind the diffraction grating, and then you will actually also start to see interference pattern on the screen. All right. When light is shown through the grating, you will actually see an interference pattern of bright dots that is symmetrical about the central beam. So if this one is showing you your diffraction grating, you shine light through the diffraction grating, the beams of light will separate. These beams of light actually represents your regions of constructive interference. All right. So if you place a screen behind, you eventually end up seeing bright dots of light that is symmetrical about your central beam. This is your central beam. So they're actually symmetrical about the central beam. Okay. So the way in which you're going to form, so needless to say, these bright dots that you have here are actually due to constructive interference, much like the case for double slits. All right. But the way they are formed is slightly different. I mean, it's similar, but with some slight variation. What we'll tell you is this. If I were to give you a diffraction grating, okay, let me just give you an example. If you recall from the double slit experiment, this one was your center line. This one is my first bright fringe. Okay, so if this one is my double slit with slit 1 and slit 2 here, under the concept of path difference that I explained to you, wave from S1 and S2 will arrive at this point, and they will interfere constructively to give you that bright spot, the bright fringe. And then there was a certain path difference to them. The difference in the path that they travel will determine whether it's constructive or destructive. In the case of the first bright fringe, what was mentioned to you was that the path difference is actually just lambda. Wave S1 will arrive one wavelength later than wave S2, they interfere constructively, giving you your bright fringe. Okay. Now for diffraction grating, it is a similar concept. Okay, it's a similar concept where you have your bright spots. You're also supposed to have constructive interference there. And then when it comes to the path difference, it's the same. All right. So what do I mean by that is, let's just say that this is my diffraction grating. All right, with many slits. And then say this one is my screen that I place behind. Okay. Say for example, this one is my center line. This is my center line. I know that I have a bright spot here, constantly interference, but some distance away, I also have another bright spot. Say this is my first bright dot or maxima lah. Okay. Now, right now for diffraction grating, as I mentioned to you, you do not have only two slits. You have many slits. So you could have S1, S2, S3, S4, S5, and so on and so forth. So when the waves from your diffraction grating arrive at this particular spot, all the waves from each of these slits must arrive at this spot in order to give you your bright dots. So what we'll say here is that S1 will arrive here, S2 will arrive here, S3 will arrive here, S4 will arrive here, and then S5 will arrive here. So you can see that they all don't arrive at the same time. There's actually a difference in the distance that they travel to that spot, okay, to this spot. There is a path difference. So in my case here, for me to have a bright dot here, my first bright dot or my first maxima, my path difference is actually also still lambda, but the path difference must be lambda between each subsequent wave. What it means by that is that between wave S1 and S2, when it arrives here to give me the bright spot, to give me the constructive interference, this path difference must be equals to lambda. And then for wave S2 and S3 to arrive at that same spot, the path difference again is lambda. And then for waves S3 and S4, when it arrives here, the path difference must be equals to lambda. You see, from one pair to another, the path difference is always just lambda. Okay, that's why here the diagram mentioned here, in the direction of the first order maximum, the waves are in phase, but each one has traveled a wavelength further than the one below it. You can imagine that if this one is your bright spot, each of these waves from each of these slits will arrive at this spot, but the difference between each of these waves in terms of the path difference is just lambda. Okay, that's why here in the notes I also mentioned this. For any maximum, the path difference between each subsequent wave must be equals to whole number of wavelengths, right? So if this one is the first bright dot, each subsequent wave must have a path difference of lambda. All right. If you're talking about the second bright spot, like this, the second bright spot or second bright dot or maxima, whatever you want to call it, the path difference must be equal to 2 lambda. between each subsequent wave. All right. Each pair of waves that arrive must have path difference of 2 lambda, each subsequent pair. All right. So that is what we mean. That's why I mentioned it's somewhat similar, but you have to look at it slightly differently. Okay. You see, between S1, S2, path difference is lambda. S2, S3, path difference is also lambda. S3, S4, the path difference is also lambda. But you compare S1 and S4, the path difference is actually going to be 3 lambda. So that one will be different. Okay, but we don't look at it that way. We look at each subsequent pair of the waves. All right, that one, the path difference is lambda. Okay. Right, but don't worry so much about this. When it comes to the exam questions, we don't really care about the path difference for diffraction grading. We don't really test you on the path difference for diffraction grading. We really only test you a lot on the path difference for double slit. Most of the questions that relate to path difference, that one is usually only for two source interference patterns. It's usually mainly used for your double slit. It's not used for diffraction grading. Okay. But when it comes to the formation of the bright spots on the diffraction grating, it does use the concept of path difference. Just that we say that each subsequent pair must be n lambda. All right. Okay. So when you have light that passes through a diffraction grating, okay, when you have light that passes through a diffraction grating, the lights will spread out. It will form certain regions of constructive interference, certain regions of destructive interference. You can see those regions or those interference pattern on the screen if you place the screen behind the diffraction grating. Okay, it will be summarized in the diagram that you're seeing in your notes right now under page 16. Okay, so basically what you do is you erase off a lot of this unnecessary stuff. Okay, so what you do is that you shine a light onto your diffraction grating like this. The beam of light will spread. This red lines here represents your region of constructive interference. Okay, so after that, you place a screen right behind the diffraction grating. What you then see is a pattern of bright dots, similar to your pattern of bright and dark fringes for double slit. Okay, but when it comes to the calculations for the patterns formed by diffraction grating, you do not use you do not use lambda equals to ax over d. This one is strictly speaking only for two source interference, such as your double slit. Okay, this is specific only for double slit or two source interference pattern. For interference pattern formed by diffraction grating, you have to use a separate equation. That one is actually d sine theta equals to n lambda. Okay, this one is specific only for diffraction gradient. And every time you see mention of diffraction gradient, you need to use this. Okay, I actually wrote it at the top part here. Okay, where we tell you d, small d here is the slit separation, n here is the order number, then theta is the angle of diffraction. So d, this is where the confusion starts to arise for some people. In your double slit, we also have d, but it's capital D. Capital D here refers to the distance between the slit and the screen. Okay, but here under diffraction grating, we also have d, but it's small d. Small d here refers to the distance between the slits. It's actually this part here. Where is it? It's actually this part here. Okay, distance between the slits. So don't mistake this D and the other D. Okay, the small d here for diffraction grating is for distance between the slits. All right, and then after that we have n. N is the order number. Okay, usually for diffraction grating, when you form the interference pattern on the screen, they are usually labeled according to order. The center bright dot is normally called the zero order. It's labeled n equals to 0. And then after that, as you go further from that center, from the center line, you start to number it 1, 2, 3, 4, 5. So if I go upwards here, this is the first order, second order, third order, fourth order, so on. And then after that, on the other side below, it will still be labeled 1, first order, second order, third order, fourth order. All right. So that is what the n there means. All right. And then the other thing here is the angle theta. Okay. Angle theta here refers to the diffraction angle. All right. We call it diffraction angle of the nth order. What do we mean by that is this. If say, for example, I'm doing a calculation that involves first order. The angle, the first order is this line here, right? Okay, this is the first order bright dot represented by this line. If I'm doing any calculation that involves the first order, the angle I use must be the angle for the first order, which means it is the distance between the center line 0 and the first order. This one is actually my theta 1. If I go and do some other calculation, but then the angle is, but then the order number I'm considering is 2, then I must use the second order diffraction angle. So what I'll do is that this one is my center line. My second order is here. This is the angle of diffraction. Okay, this is what we mean by the angle. All right, it's actually the distance between that order that you're considering and the center. All right. Okay, then another thing that you should know here is what are the differences between your what are some of the differences between the interference pattern formed by your double slit and your diffraction grating. That one is summarized here. Okay, so normally we tell you that the bright dots refer to a maxima are more widely spaced than a double slit. Okay, you could be using red light. You shine it through a double slit, and then you get a pattern of interference fringes, bright and dark fringes. You notice that there's a certain spacing between the bright fringes, correct? If you shine that same light, say red light, to a diffraction grating, you're still going to get a pattern of interference fringes represented by dots, bright dots on the screen. But generally speaking, we'll tell you the distance between the dots is actually much wider than that of a double slit. That's what this statement means. They are more widely spaced than with a double slit. Okay. So just now I mentioned that the central fringe is called the 0 order. The next dot is the first order maximum and so on. And then another key difference here between double slit and diffraction grating is this. The maximas are not equally spaced, and the angles between the adjacent maxima increases with order number. So remember last time in the summary for double slit, I mentioned that in the summary for double slit under page 12, I mentioned that the X is the same. If let's just say under page 12, there was a summary of the double slits, right? Okay, I told you the fringes are equally spaced. The distance between adjacent fringes remain the same regardless of distance from the center line. So what was I saying then was that if you go further away from your center line, the distance between the fringes actually do not change. Okay. So if I look at the diagram on the right hand side right now, if I go further away from the center line, this X and this X will always remain the same. I can also go on to the next pair of fringes. The X will also remain the same. They won't change. Okay. But when you're talking about a diffraction grating, okay, if you talk about diffraction grating, let me just erase everything here. This distance x1 and this distance x2 and maybe another distance x3, what will happen is that they're not going to be the same. X3 is not the same as x2, is not the same as x1. Instead, x3 is going to be more than x2, is going to be more than x1. That's what this statement here means. They are not equally spaced, okay? And the angles between the adjacent maxima will increase with order of magnitude. So it could be that between here and here, your angle is 10 degrees. But then after that, for this one and this one, the first order and second order, your angle is not the same. Maybe it becomes 20 degrees. And then after that, you go on to the next one, between the third order and second order, your angle becomes, say, maybe 40 degrees. All right. So it's because the angle keeps increasing. That's why the distance between the fringes or distance between the bright dots keep increasing. They won't be equally spaced. Okay. So that is one thing different between double slit and diffraction grating. Double slit spacing will always be the same. Diffraction grating spacing will not be the same. Okay. It will tend to increase with distance from the center line because the angle keeps increasing. All right. And also for diffraction grating, the maxima tends to be a lot sharper and brighter than double slits. For double slits, you tend to see the bright fringes as being a bit fuzzy, but for diffraction grating, you tend to see the bright dots as quite sharp. All right. Okay, so that is one of the main differences for diffraction grating. Okay, then I go through some little parts here again for you. All right, just now I mentioned to you slit separation is represented by the symbol small d. A lot of times when you're doing calculations for diffraction grating, they may not give you the slit separation directly. Instead, they tell you something else. They will tell you that the diffraction grating has don't know how many number of slits per unit length. Maybe they tell you, okay, the diffraction grating has 100 lines per millimeter or 1200 lines per millimeter. That one is this quantity here. Okay, it tells you how many lines are there in a certain distance. You want to find slit separation is this. So the relation between the number of slits per unit length and slit separation D is given by this equation. D is 1 over n. All right. Is something similar to this. Why is it D equals to 1 over n? If I tell you you have 100 lines per millimeter, okay, that means 1 millimeter has 100 lines. So D would be akin to you taking 1 millimeter divided by 100 lines. So this one will give you 1 times 10 power minus 2 millimeter. Okay, that's the understanding here. I could also give it to you in some other values. Let's just say 1200 lines per centimeter. That means 1 centimeter has 1200 lines. So I want to find the slit separation. I take 1 centimeter divided by 1200. Okay. I'm basically taking 1 centimeter divided by 1200 lines. So I'm gonna get 8.33 times 10 power minus 4 centimeter. Okay, so these are the slit separation. So I may mention here, if n is given in number of lines per millimeter, then d will be in millimeter. Similarly, if n is number of lines per centimeter, then d will be in centimeter, because the understanding is that you're taking whatever unit of the per unit length divided by the number of lines, your unit will be following the original unit. Okay, if it's something per millimeter, the d will be in millimeter. If it's something per centimeter, then your d will be in centimeter. Okay, so be mindful of this. All right. Okay, then the next thing I just want to talk about is when you do your questions on diffraction grating, you will also be asked to calculate one of two things. Calculate the maximum possible order number, or calculate the total number of bright dots and maxima. So just now I mentioned to you, when you shine light onto your diffraction grating, your light will tend to spread out. And then after that, you place a screen behind and you see a pattern of bright dots. So I mentioned specifically to you, the bright dot or maxima at the center is zero order, and then from there you start to label it first order, second order, third order, and is symmetrical about the center line. So the order number cannot increase indefinitely. It will reach a maximum eventually. So you cannot go up to the 99 order number. Depending on the wavelength that you use, depending on the slit separation that you use, you will eventually reach a maximum order number. You can only produce a certain order number, maximum order number. So some questions will ask you to calculate what is the maximum order number. All right. So what you do is that you use your diffraction grating equation, where we tell you d sine theta is n lambda. N is in turn going to be, what we'll tell you is that n lambda is over d is equals to sine theta. Now you know that sine theta can never be greater than 1. The maximum value of sine theta is just 1. It will never be greater than 1. So this equation becomes like this. Okay, because sine theta cannot be more than 1, the equation becomes this: n lambda over d less than or equal to 1. So n max is actually going to be d divided by lambda. All right, your maximum order number can be found from this equation: the ratio of your slit separation divided by your wavelength. Okay, sometimes in your marking scheme, they don't use the inequality equation. They just say n max is actually d over lambda. You will eventually see this being used in your marking scheme. Okay, so to find your maximum order number, you need to use the ratio of d over lambda. Whatever value you get, this is very important. Whatever value you get, you must always round it down to the nearest integer. What do I mean by that is that it could be that your n is maybe 4.1. This one rounded out will just be 4. But what if your n is 4.8? In normal maths, you would have probably round this to 5. This one, no, don't ever do this. You round it down to nearest integer, meaning to say it's supposed to be 4. Okay, so this one, just be careful of this. When it comes to finding maximum order number, you will always need to round it down to the nearest integer. Don't round it up like you do normal maths. Okay, so that part is okay. All right, then the last one that I just need to mention before I end the class for you is that sometimes rather than finding maximum order number, they will ask you to find the total number of bright dots or maxima. So remember, one of the first things that I mentioned to you just now was that the interference pattern that is formed is usually symmetrical about the center line or the central maximum. So meaning to say, normally you have 2 first order maxima, 2 second order maxima, and so on. You can actually see it over here. Okay. You have 1, 2, 3. You also have 1, 2, 3. Okay. So you see this one here, third order is your n max. Okay, let's just say this is your n max right now. If we are asked to find the total number of bright dots or maxima, it means they want you to find what is the total number here. So an easy way to do that would be to take the highest order number, multiply with 2, plus with 1. Okay, because you see here, first, second, third, this one is already 3. If you somehow multiply with 2, you're going to take into account this one too. All right, but there's another one that you haven't taken into account, which is the center one. So that's where your plus 1 came about, is because you're adding the 0 order inside. So this one will give you the maximum order. This one will give you the total maxima, total number of maxima. Okay, so there's a difference between calculating maximum order number and calculating the total number of maxima. This one you need to read carefully the question, what they want. All right. Okay, have a look at page 5 of your worksheet. All right, and this one is a question on diffraction grading. All right. So what you have here is they say state what is meant by diffraction and by interference. Diffraction can just be the spreading of a wave as it passes through a slit or past an edge. Actually, if you just write this sentence, spreading of a wave as it passes through a slit, this one alone is already enough. You don't really need to talk about the wave passing through an edge. This one is optional. As long as you write one. The most common one is you say passing through a slit. Okay. And another thing here is when you're talking about diffraction and in terms of the definition, try to avoid using bending of wave anymore, all right? Because the more recent examiners report says that they would rather candidates don't write bending of wave, because bending of wave is more for refraction, not diffraction. Okay, diffraction is spreading, all right? Okay, then after that, when you look at what is meant by interference, this one is really talking about superposition. We can say that when 2 or more waves meet, the resultant displacement is the sum of displacement of each wave. This is actually following the definition of your principle of superposition. All right, so this one alone is 2 marks. Okay, so that one is all right. Then after that, you can have a look at part B. All right. For part B, they say that light from a source S1 is incident on a diffraction grating. Okay. So they say this one is incident on a diffraction grating. A lot of times when you read your questions, try to identify first whether is it a double slit or diffraction grating, because it will change the equations that you need to use. All right. So since you already see that it's a diffraction grating, all right, they say that the light, sorry, I need to go down or clear off everything. They say that the light has a single frequency of 7.06 times 10 power 14 hertz. The diffraction grating has 650 lines per millimeter. Calculate the number of orders of diffracted light produced by the grating. Don't include the 0 order. Show your working. All right. So when they ask you to find out the number of order, this is actually asking you to find the maximum order number. In the notes under page 16, no, not page 16, under page 17, I mentioned to you, if you have a diffraction grating, your light is shown to the diffraction grating, that light will tend to split up like this. These lines here is representing your lines of constructive interference, such that if you go and place a screen at the front, that's how you end up looking at the dots. on the screen. Okay, so I mentioned to you the center one, the center bright fringe, the center bright dot, center maximum is normally having an order number of 0. It's only when you go further away from the center line that you start numbering it. This one is first order, this one is second order, and so on and so forth. So the order number cannot increase indefinitely. It will reach a limit eventually according to the arrangement that you have. So you want to find the maximum order number, that one I mentioned to you, you will be using this equation, but commonly you will change it to this form. N max is equals to D over lambda. To find the maximum order number, you take the ratio of D divided by the wavelength. And then after that, you need to round down the value to the nearest integer. Never ever round up. Okay, always round it down. This is a bit special for diffraction grating. All right, so then you look at this question now. They want the maximum order number. So you know that this one is a diffraction grating. I'll just skip around first, all right? You know that this one is a diffraction grating, so you need to use n lambda equals to d sine theta. So I mentioned to you at maximum order number, theta will be 90 degrees. So this one, theta will be 90 degrees. This indirectly means that sine theta, which is sine 90, will be equals to 1. Okay, so this one is 1. That's why you get n lambda over d, n lambda equals to d. So n is actually d over lambda. I think I better write this, n max. Okay. If you want to, you can write n max lambda equals to d. All right. The ones in the notes makes use of an inequality equation, inequality symbol. You can actually also replace it with this. Okay, this one will n max less than or equals to d over lambda. You can also actually make your life a lot easier. You can just write it as this. All right, same thing. Okay, the derivation part like this one here is actually not required to be shown, but if you want to, you can just show it now because the questions here say show your working, so might as well just show. All right, so you get n max equals to d over lambda. All right, but before you can proceed, you will notice one thing. You actually cannot proceed from here because your question did not give you the value of d and it did not give you the value of lambda. The question never say any of those values for you. So you actually have to find them out. Where can you find them? Firstly, if you want to find out the wavelength, you can actually use V is equals to F lambda. This is a light, it is EM radiation. So therefore the speed must be 3 times 10 power 8. You also know the frequency. So just sub the values for the speed, for the frequency, and you get the wavelength. So you tackle one part already. Now another part will be finding the D. The D is actually the distance between slits. So if this one is your diffraction grating, D here refers to the distance between your slits. Usually your diffraction grating will be given in terms of number of lines per unit length. Okay, so D is the distance between slits, and then after that there's another symbol called N. That one is actually your number of lines per unit length. That would be this one here. They've given you the diffraction grating has 650 lines per millimeter. This is your N right now. It is your number of lines per millimeter. So what was the relation between N and D? In the notes, it was written that D is actually 1 of N. Okay. So if you take 1 divided by N, you will be able to get D. But then be careful about the units. If I say D is equals to 1 over N, and I take 1 divided by 650, I'm actually going to get the value in terms of millimeter. Because the idea is that I'm saying 1 millimeter divided by 6 divided over 650 lines. So I'm going to get the answer in millimeter. So I'm getting the answer in millimeter, but I need to change it to meter. So I multiply with 10 power minus 3, giving me 10 power minus 6 here. All right. So over here, you see the D, actually I already wrote it out, 1 divided by N. Okay. So it's actually 1 divided by 650. But why is there a times 10 power minus 3 here? Is because I changed it to millimeter. It's a bit it's similar to this. I'm saying 1 over 650 times 10 power minus 3 because I'm changing to meter. That's why you see it's 10 power minus 3 divided by 650. The 10 power minus 3 is because I'm changing it to millimeter. All right. So you have the value of D, you have the value of wavelength. Eventually, you will get the value of Nmax as 3.65. So remember, I mentioned to you, don't ever round up your values regardless of what you see. Always round it down. This one, by right, normally you would round it up to 4. But I mentioned to you specifically for diffraction grating, when it comes to maximum order number, just round it down. So your maximum order number is actually just 3. Okay. So that one is for this. Okay, then if you are okay with this, then maybe I move on to the next section, part C. All right, so I'll clear off everything here. Now you have a second source S2 that is used in place of S1. The light from S2 has a single frequency lower than that from S1. State and explain whether more orders are seen with light from S2. Okay, so the conclusion you could have gotten from doing this question was that Nmax is actually D over lambda. When you did this changes here, you actually did not change your grating. You did not change your diffraction grating, you only change your source. All right. So here, since you did not change your grating, the distance between the states ought to remain the same. D here is constant. Therefore, Nmax is inversely proportional to wavelength. And here they told you frequency lower. So frequency is inversely proportional to wavelength. If frequency is lower, that means wavelength is higher. So from here, wavelength increase, therefore Nmax should drop. So therefore your answer is you have a greater wavelength because you have a lower frequency, therefore you have fewer orders seen. This is the, whatever you see here is kind of like the idea behind this. All right. This one I think is only 1 mark. Okay, yeah, so that's why the answer is a bit short. All right, so that one should be okay. All right, then if this is fine, page 5 is okay, then we go to page 13, question 28. All right. Okay, we go to page 13, question 28. Okay, this one. So I'll clear everything off. Question 28, page 13. All right. You have a diffraction grating with n lines per unit length and is placed at 90 degrees to monochromatic light of wavelength lambda. What would be the expression for lambda, the angle normal to the grating at which the third order diffraction peak is observed? Okay. So this one is your diffraction grating. Your light is this one. They say that your light is at 90 degrees to the grating. Basically, what they said here was that diffraction grating is placed at 90 degrees to monochromatic light of wavelength lambda. So this is your light. You're placing your grating perpendicular to it. That's what it was saying. All right. So light passing through diffraction grating, it will tend to speed up like this and then form an image on your screen, giving you something like this. All right. So they tell you what's the expression for theta, the angle to the normal to the grating at which the third order diffraction peak is observed. Now, angle to the normal to the grating, this one seems pretty confusing. It's actually referring to this. You see, the grating is this one. Normal to the grating is actually this one. Okay, this is what they mean by the normal to the grating. So what they're asking right now, what's the angle theta, which is the angle to the normal of that grating? Basically, they're asking what is the angle to this line here, all right, to the third order. So if my line is like this, I need to draw more lines. This is n power 0, and sorry, n0, not power 0, n0, n1, n2, n3. They want an expression for this angle between the normal and the third order. This is your third order. They want the angle between the third order and the normal, which is this one. All right. So because this one, you already identified that it is a diffraction grating d sine theta equals to n lambda. Because you're dealing with third order, that means n is equals to 3. So this one will be 3 lambda. And then your d, they never gave you the d, but then they gave you n. The relation between d and n was that d is 1 over n. So this one is 1 over n sine theta. So eventually you will get this answer. Sine theta is 3 n lambda. Answer is C. Okay. So that one is okay. Right, then next one that we can do, page 20, question 26. Right, page 20, question 26. So let's go to that. If we go to page 20, question 26, this is what you will have. Right, so I'll clear this one off. Page 20, question 26. So what you have here is that they say monochromatic light wavelength 5.3 times 10 power minus 7 meter is incident normally or perpendicular to the diffraction grating. The first order maximum is observed at this angle, 15.4 degrees to the direction of incident light. What's the angle between the first and second order diffraction maxima? Okay, so you want to visualize what's happening here. Light passing through your diffraction grating. And then this is your screen. I just draw a single line. This is your screen. The light will diffract like this, like this, like this, like this, like this, like this, and like this. N0, N1, N2, and 3. So the question says that they want the angle between first and second. Angle between first and second that they're referring to is this one. Okay. If you use the equation d sine theta, let me just give you an example. If you use the equation d sine theta equals to n lambda, for first order, d sine theta 1 n lambda, this theta 1 is this one. If I talk to you about the second order, d sine theta 2 lambda, theta 2 is this one. Okay, so that's the angles here. If you're talking about using this equation straight, your theta is measured from the center line. Okay, so theta 1 is from center line to your first order. Theta 2 is from your center line to your first order. But the angle they want here right now is the angle between first and second order, this one. So this angle that you want is actually angle between theta, is actually theta 2 minus theta 1. All right. You need to find out theta 2 and theta 1 right now. Okay. So there's an easy way to go about this. Now, when you look at this question here, you have two different cases, right? Okay, all right, wait, sorry, I need to admit the new student. Okay, generally you're here. Okay, generally you just joined. We're under page 20 of, the worksheet, question 26, all right? Okay, now back to what I was talking about. When you're talking about the first and second order, the equation d sine theta equals to n lambda applies to both. All right. So now if you want to make a comparison between both cases, there are certain variables that are common. The first variable that is common is d. The second variable that is common is lambda. All right. So from here, you can actually say this. D and lambda constant would mean that sine theta is actually directly proportional to n. Okay, d is constant, lambda is constant, sine theta is actually proportional to n. From here, you can actually start to do this. Sine theta 2 over sine theta 1 is equals to n2 over n1. Now, you actually know angle theta 1 already. They've given it to you as 15.4. So sine theta 2 is what theta 2 specifically is what you want to find. So you have sine 15.4 equals to 2 divided by 1. You try to solve this and find out what is your theta 2. So let me just use the calculator. 2 times sine 15.4 arc sine of 2 times of sine 15.4 arc sine of the answer. Theta 2, you're going to get 32 degrees. Okay, you're going to get 32 degrees. So when you want to find the difference in angle between the first and second order, your difference in the angle, theta 2 minus theta 1, will be 32 minus 15.4, giving you 16.6 degrees. The closest answer to that is actually this one. Okay, it's just a difference of 0.1. This is supposed to be the answer. So answer is C. All right. Okay, so this one is all right. Then I move to the next question. Okay, page 20 is okay. Then you go to page 22, question 26. All right. Page 22, question 26. Right, so let's have a look at that. Page 22, question 26, which is this one. Right, so I'll just clear off everything. Question 26. All right, now, you have a parallel beam of light of wavelength 450 nanometer incident normally on a diffraction grating which has 300 lines per millimeter. What is the total number of intensity maxima observed? Okay. Total number of intensity maxima observed. All right. So what you have here, they are actually not just finding Nmax, they're actually finding this one. Okay, in your notes under page 17, I mentioned to you that your questions will sometimes ask you what's the maximum possible order number, or they'll sometimes ask you what is the total number of maxima instead. The question that you're looking at is talking about this. They want the total number of maxima. Okay, they're not just asking for maximum order number. They want the total maxima that you can see, right? So based on what you know just now, d sine theta equals to n lambda, n max when sine theta equals to 1. So you get d equals n max lambda. So n max is actually d over lambda. Right, you have wavelength and you should have the value of d. Okay, now this value that you have here, 300 lines per millimeter, is not d, it is n, and this is in millimeter. So if you want d, d will be 1 over n, 1 over 300, but it's in millimeter because 1 millimeter divided by 3 lines. You want to change it to meter. So you'll be 10 power minus 3 over 300 because you're changing to meter now. Okay, so this is the expression for D. So now you have this, you can sub in everything. N max is going to be 10 power 3 divided by 300 divided by wavelength, 450 times 10 power minus 9, 10 power minus 3 divided by 300. Wait, sorry. Minus 3 divided by 300 divided by 450 divided by 10 power minus 9. You're going to get 7.4. Okay, you're going to get 7.4, but you need to round it up. Not round it up, sorry, round it down. Therefore, n max is 7. This is the maximum order number. But the question wants total number of intensity maxima. So total number of maxima is going to be 2 times of n max plus 1. 2 times 7 plus 1 gives you 15. So answer is D. Alright. So why do you need to multiply by 2 times of your n max? Why do you need to plus by 1? Is because of what I mentioned to you inside the notes already. This one is again under page 17 of your notes. When your beam of light shines through your diffraction grating, your light will diffract, giving you these beams. Okay. They are symmetrical about your center line, which is this one. And then you start your numbering after the center line. The center line itself is 0. After that, you start numbering. Okay. When you find maximum order number, you're only finding the maximum order for one side. So if you want to take into account the other side, you have to multiply by 2. But then you also need to take into account the 0 order that wasn't taken into account. That's why you plus 1. Okay, that's why your answer is this. All right. Okay, so that one is all right. Page 22 is okay. Then we jump to page 24. All right. Next one will be page 24. Question 27. Right, so this one is okay. Right. Page 24. Question 27. All right, now you have a diffraction grating with n lines per meter that is used to deflect light of various wavelengths. The graph shows you a relation between the deflection angle theta and lambda for different wavelengths of the nth order interference pattern. What is the gradient of the graph? This one you know is diffraction grating. So d sine theta equals to n lambda. And then notice how this graph looks like. Y-axis is sine theta, x-axis is lambda. What you want to do is that you try to make this equation in the form of a straight line equation, following the general equation of a straight line. So if you go and play around with it, you should get sine theta equals to, oh wait, before I go to that, let me just change this. This is 1 over n. Then sine theta equals to n lambda. Okay, notice that this one is already per meter. So I don't really need to multiply anything to change it to meter. I can just leave it as this. The case before this was that I multiplied by 10 power minus 3, but that one was because they were in millimeter. I had to change it to meter. That's why it's multiplied with 10 power minus 3. But this one is already in meter, so I don't need to do anything. Okay. So this one eventually gives me sine theta n times n lambda. So equate the equation of a straight line y equals to mx plus c, where y-axis is sine theta, lambda is x, gradient is going to be this one. Okay, but looking at this equation alone, you can actually see that it's supposed to be a straight line through origin, because your y-intercept here is non-existent, so it's going to be a straight line through your origin, which is what you're seeing right over here. Okay, your gradient is going to be, this is number 1. Number 2, gradient would be equals to n times n. They want the expression for the gradient, so answer is A. Big N multiplied with small n. All right, so this one is okay. Then we go to structured questions, page 26. All right. Right, just have a look at page 26. All right. Okay, so page 26 would be this one. What do they have here? Okay, page 26 is pretty straightforward. Okay, just have a look at page 26. Now, they tell you light over single wavelength is incident on a diffraction grating. Explain the part played by diffraction and interference in the production of first order maximum in the diffraction grating. Now, the diffraction occurs at the slits, all right? The interference occurs after the light spreads out from the slit. And then when they spread out from the slit and interfere with each other, that's how you form your regions of constructive and destructive interference, which I think I've shown many times already, so I don't think I will show right now. So let me just open the answers for you. This is June 2026, June 2016 P22, question 5. The correct question. Right, so what is the part played by diffraction? Diffraction causes the spreading of light at each slit. What does interference do? The overlapping of the waves where path difference is lambda produces the first order. Oh, okay, this one you have to refer to this. Okay, the diffraction part, spreading of light takes place at each slit. This one is okay. You don't need to really explain too much about it. But the second part, when they talk about the interference, you say overlapping of the waves to form a new resultant wave where the path difference is lambda produces the first order. Okay, because they say here, explain the part played by these two in the production of the first order maximum. Okay, how did the interference produce the first order maximum here? Okay, you say something about the waves overlap with path difference of lambda to produce the first order. Okay, this one was briefly explained last week when I mentioned to you under page 15, if I'm not mistaken. All right, when you want to have a particular interference at a particular order, let's just say first order, the path difference between each subsequent wave must be lambda. If you're talking about second order, the path difference between each subsequent wave is 2 lambda. So for any n order, the path difference must be n lambda. Okay, so that one is this. When you want to form an interference pattern at any of the order number, say n is 1, all the waves from each of these slits here must arrive at this point and interfere with each other. The double slit one that you've done before this only had to consider waves from two sources. But for diffraction grating, you have to consider waves from all the sources. At this point here, the waves from all these sources overlap at this point. Okay, but one after another, the path difference will just be lambda. But if you're talking about the second order, same thing occurs. The waves from all these sources will overlap at this point, but they won't arrive at exactly the same time. They will arrive later than the other. So the path difference between each of them must be, in your case, 2 lambda. All right, that was the idea here. So here they say overlapping of the waves so that the path difference is lambda produces first order. That is the answer. Okay. Okay, so if this one is okay, then maybe I go and do the part B. Okay, diffraction grating illustrated in figure 5.1 is used with light of wavelength 486 nanometer. All right. The orders of the maxima produced are shown on the screen in figure 5.1. The angle between the two second order maxima is 59.4. Calculate the number of lines per millimeter of the grating. Okay. They want to find out the number of lines per millimeter of the grating. So right now, when you look at this one, this angle here, you already know that it's for second order, all right? But be careful about the angle that they just stated for this one. If you're talking about d sine theta equals to n lambda, I mentioned to you before that angle theta is measured between center line and end line, okay? It's measured between the center line and the maxima line. Now, maybe I just write as that, okay? It's measured between the center line and the end maxima line, all right? So right now, the 59.4 that you see is this one. It is between the two second orders. That is correct. Okay. Why did I suddenly have this? It's between the two second orders, but this one is not theta itself. Theta by right should be from the center line. This one would have been your theta from this equation. Okay. So your theta here is actually 59.4 divided by 2 when you're talking about the second order, right? So just be careful of that. So right now they want you to find the number of lines per millimeter. Use diffraction grating equation. Change d to n. Your angle, take half of it because you want this angle. Measure from center line to the n order maximum line. And then you're talking about second order now, so this n is 2. Your wavelength, I think they already told you, 486 nanometer. So just sub everything in and you should be able to get the answer. Okay. You will get the answer in millimeter, in meter. Okay. So what you're having here is 5.09 times 10 power 5 lines per meter. Okay. N is 5.09 times 10 power 5 lines per meter. You want to change it to millimeter. You can think of it as something similar to this. 5.09 times 10 power 5 over 1 meter. This one you want to change to millimeter. So it is going to be 5.09 times 10 power 5, 10 power 3 meter. Sorry, millimeter. 1 millimeter is 10 power negative 3 meter, right? So 1 meter is in turn 10 power 3 millimeter. Okay, that's why you have this. That's why it's divided by 1,000 to get the answers in per millimeter. Okay, so that should be fine. Right, then this one, no other issues. Then we look at, say, page 30, question 29. Okay, next one, look at page 30, question 29. Page 30, question 29. This one seems very simple. Okay. If we look at page 30, question 29. Page 30, question 29. Okay, this one I think I'll just breeze through it very quickly. Diffraction grating is used to measure the wavelength of monochromatic light. The spacing of the slits in the grating is 1.15 times 10 power minus 6. Angle between first order diffraction maxima is 60 degrees. What is the wavelength of light? This is actually like that same question just now that we've done. All right. They say first order, the angle between first order is 60. But when you're talking about the theta is not 60. The theta will be 60 divided by 2, giving you 30 degrees. Right? The one the wavelength of light, d sine theta n lambda. The value that they given here is actually d itself. All right, so that's why read your questions carefully. Sometimes they will give you a number of lines per millimeter, per meter, or just the spacing itself. In your case, they're giving you the spacing itself. 1.15 times 10 power minus 6 sine 30 equals to n equals to 1. N is 1. So then you get your lambda. So 1.15 times 10 power minus 6 times sine 30. You're going to get 5.75 times 10 power minus 7 meter. Change to nanometer. 5.75 times 10 power minus 7 divided by 10 power minus 9 is 575 nanometer. Let's say C. Okay, so this one is all right. Okay, then after that, structured question again, page 32. Okay, now this one is structured question again, page 32. Have a look at page 32 of your worksheet. Okay, I'll continue discussing until our first hour is up before I go to stationary wave. Okay, page 32, November 16, P21. Question 5. State what is meant by diffraction of wave. When the wave passes through an aperture or slit, it spreads into the geometrical shadow. This one we've actually done it before. Okay, sometimes when you look at the definition for diffraction of a wave, you will always see the part where the wave passes through an aperture, it spreads. In some cases, you may see the another addition to the statement where they say it spreads into the geometrical shadow. Okay, now what is geometrical shadow? Is something that looks like this. Let me just draw it out for you. If I have an aperture or slit like this is my aperture or slit. I have a wave that is moving towards that aperture or slit. What you know was that this, provided that the gap and the wavelength are comparable, the wave will spread like this. Significant diffraction will look like this. Now, the part where they say it spreads into the geometrical shadow is actually this part. Okay. This part here and this part here is actually what we know as the geometrical shadow. You can think of it as just the shadow behind the slit, that's all. Okay. The geometrical shadow is actually these little black regions that I've kind of indicated. All right, it's kind of like the shadow behind the slit, right? So that's why we say that when your wave passes through an aperture or a slit, it spreads into the geometrical shadow. It's actually spreading into the shadow behind the slit. That's what it meant, okay? In older past year questions, spreading into geometrical shadow is actually a marking point in itself, okay? But the more recent ones, they don't really bother about this one anymore, okay? Even in the notes that I just wrote for you, you notice that this statement isn't inside, okay? But just in case when you're doing the older past year questions, you will sometimes encounter a case where this one is actually inside your marking scheme. It's a point in itself, all right? So I leave it to you whether you want to include it inside or not, all right? Okay, so let's look at part B. I mentioned that laser light of wavelength 500 nanometer is incident normally on a diffraction rating again. The resulting diffraction pattern has diffraction maxima up to and including fourth order. It is up to n equals to 4. So now calculate for the diffraction rating the minimum possible line spacing. Okay, this one is asking for big N, capital N. All right. So here you can actually just say something like this. N lambda is d sine theta. I know that maximum order number sine theta will be equals to 1. So this one is 4 times 500 times 10 power minus 9 equals to d multiplied with 1. So d, oh sorry, just now I made a mistake here. Minimum possible line spacing isn't big D, it isn't big N. It's actually asking for D, sorry, my mistake. Okay, they're asking for D itself, all right? So back to this equation, 4 times 500 times 10 power minus 9 equals to D times 1. You're going to get D equals to 2 times 10 power minus 6 meter. All right. So this one is okay. All right. They don't want the N. They don't want the line spacing, but they don't want the number of lines per unit length. They want the line spacing itself, which is D. Okay. Sorry about the mistake. All right. Okay. Then after that, they tell you now light in B is now replaced with red light. Stay and explain whether this is likely to result in the formation of fifth order diffraction maximum. Okay. Now you replace the light with red light. Stay and explain whether this is going to result in the formation of a fifth order maximum. Okay, so what can you say from here? They gave you the laser light of wavelength 500 nanometer, but they didn't state to you the color. Okay, they never state to you the color. So, but then after that here they state the color of the new light that they use. This one you will have to refer back to your visible light spectrum. Okay, you have to refer back to your visible light spectrum. Visible light spectrum is Roy G. Biff. Going towards the right is where wavelength decreases. Now, red light is over here. This one would be the biggest wavelength, 700 nanometer. Violet light would be the smallest wavelength at 400 nanometer. Because I mentioned to you that wavelength of visible light, which you must know, is 400 to 700 nanometer. 4 and 7. You go back home from college at 4. You need to leave your home to college in the morning at 7. Okay, so that's how you kind of remember the 4 and 7. All right, so you have 500 nanometer, but I know you are red light. Red light is already 700, so definitely I can say that wavelength of red light is longer than 500 nanometer. All right. So what does this then do? Would it allow me to form a fifth order diffraction maximum? Okay, so how you can see this is by looking at this. What happens to the angle? If you look at your diffraction grating equation, d sine theta equals to n lambda, the only thing you've changed is just the light. You did not change anything else about the apparatus. That would have meant that you did not change the d, you did not change the, wait, how would I say this? ND are constant. Sorry, n and d are constant. Something is wrong with this. Okay, your n and d are constant. D is constant because the grating did not change. Okay, the n here I say is constant is because let's just say you're comparing the same order number right now. Okay, say maybe you're comparing the first order number. All right, each order is now greater at a greater angle. What it means here is for same order number, each the angle is greater. For same order number, the angle is greater. Okay, what do I mean by that is something like this. If this is your light, sorry, that passes through your diffraction grating. Okay, maybe I better make it a bit more realistic. Say if I shine green light onto your diffraction grating, it will form an image on your screen like this. Okay, so say this is n equals to 0, this is n equals to 1. All right, this one is the angle theta 1 for first order using, say, green light. If I change this to red light, I shine it through my diffraction grating, I'm going to get something similar. But my red light, the first order will be spread out even more. This one will be, again, n equals to 0 for my red light. But the red light, the n equals to 1, will be somewhat further. Okay. You see, the n equals to 1 for green light was this one. This was its angle. But the n1, the first order for the red light, again for first order, is bigger. This one is my theta 1. Okay, that's what this statement here was actually trying to refer to. Each order is now at a greater angle, or rather for same order number, the angle is greater. So this pattern that you see here repeats itself for all the subsequent order numbers. For second order, you see that red light is even further. For third order, you see that red light is also still further. Okay, so the way to look at it is by looking at this. All right, d sine theta equals to n lambda, n and d is constant. That means lambda is proportional to sine theta. If your theta increase, your sine theta increase. Therefore, theta also increase. The way I look at it for my graph is this. If you look at your sine theta graph, it looks like this, right? You look up to a maximum value of 90, okay? You will notice that if I look up to a maximum value of 90, if my sine theta increases, my theta is increasing. Say this one is sine theta, and this is theta, right? If I just look at to an angle, maximum angle of 90, you'll notice that the more I move towards the right, sine theta is increasing, but my theta is also increasing. That's why I can make this conclusion here, which in turn gives me this. Okay, so since everything is now at a greater angle, it's unlikely your fifth order maximum can be formed. Because you see, how should I say this? if this one was your whole screen right now, the green light you have could only go to a certain maximum, maybe n to 4. Okay, this is a very horrible drawing to show that. Let me show you it in a different diagram. If this one is a diffraction grating, this one was green light. You shine it onto the screen. You have n equals to 0, n equals to 1, n equals to 2, n equals to 3, and then n equals to 4. Okay. So if you change to red light, you see this is the maximum that you can really see on the screen. But then if let's say you replace it with red light, just now I mentioned to you for the same order, for the same order, the light for red, the order number, for the same order number, the angle will be greater. So if you're talking about for the red light, n equals to 4 itself, it will actually be much further, okay, from when compared to the green one. So the question now is asking you, is it likely going to give you a fifth order? Your fourth order itself is really going to be out of the range of the screen already. So what more to say fifth order is not likely, okay? Therefore, your fifth order maximum cannot be formed. That is the understanding here. Because they already say that the fourth order is the maximum that can be formed on the screen right now. So if you use a different wavelength of light, whose wavelength is longer, which in turn causes the angle to be greater for each order or for the same order, logic will tell you you can't even form a fourth order. Logic will tell you it will be very hard to form even a fourth order on the same screen. So fifth order definitely cannot be formed. All right. So that is what you do here. So far, so good. Now you might want, if you're thinking whether can you also do this, d over lambda. Now, if you try to use the equation n max is equal to d over lambda, you probably will also get that same conclusion. D is 10 power minus 6. Lambda is red light is 700 times 10 power minus 9. So 2 times 10 power minus 6 divided by 700 divided by 10 power minus 9. You're going to get 2.85. It's actually 2 only. Okay. The ones that you see here is actually another way of explaining the same thing. Okay, just now when we were talking about all the questions regarding the maximum order number, the equation that I always use was this one, isn't it? All right. If you try to use the same thing over here right now, you have gone to the same conclusion. Just now, n max is the ratio of the d to wavelength, right? I know d as this one. I know wavelength of red light as 700. So eventually I get this answer, 2.85. I round it down, I get 2. Okay. If you want to explain it in this manner, I would say it's also sensible. All right. Maybe you will understand this one better. But the one that the marking scheme used is the one that I just wrote here. Okay, this is another way of looking at it. Okay. So that one is all right. Okay, then maybe I do one last question on diffraction grating before I give you guys a short break, and then I go to stationary wave. All right. Okay, so let's have a look at page 12. There was one small part that I haven't really gone through with you when it comes to your diffraction grating. Refer back to page 17 of your notes. Okay. Now, all the cases of diffraction that we have gone through so far was just using monochromatic light. meaning to say light of a single wavelength or single colored light. What happens if you try to use white light instead? Right? What happens if you try to use white light instead of monochromatic light? So if you try to shine a beam of white light onto your diffraction grating, you will still get interference pattern on your screen. All right? But the interference pattern that you see on your screen right now would consist of a white central maximum and a series of color spectra on either side. So what you will see on the screen is that you shine white light at the center, you will still see white. But then after that, when you go further away from the center line, you start to see rainbow colors. Okay, you start to see rainbow colors. Before this, if it was just monochromatic light, like the ones that you see in the screen here right now, you shine red color light, you're gonna get a red color dot at the center, and then the subsequent ones from the center line will also be a red color dot or red color fringe, if you would. But now you use white light, the further you go away from the center, you're actually seeing rainbow colors. All right. Now the reasoning why you're seeing rainbow colors is mainly due to the fact that white light has different wavelength, different colors. The wavelength being different will cause different colors. So what we'll tell you is that because you have different wavelength, different wavelength causes different angle of diffraction. Okay, we know this from the question that we just done, the ones that we just did just now. This one I mentioned to you what happens when you go and change your light from 500 nanometer to red light. If you did not change anything else, you will notice that your angle for the same order will be larger, isn't it? So you can come to the conclusion that different wavelength produces or causes different angles of diffraction. All right. So what you can think here is that because your white light consists of 7 different colors, 7 different wavelengths, they're gonna diffract by different angles. That's why they seem to be spread out, forming a rainbow color. Red color will diffract by different angle, so it hits one spot on the screen. Blue color would diffract by a different angle, so it hits a different spot on the screen. Yellow color would diffract by another different angle, so it hits another separate spot on the screen. So all in all, you see the 7 different colors hit different spots on the screen. That's why you see it's rainbow. Okay? That was the explanation for this. Why is it rainbow color in the first place? Different wavelength causes different angle of diffraction. That's why it caused the rainbow color here. All right? It causes different angle of diffraction. Maybe I write here. Therefore, it appears on different spots, different positions on the screen. Therefore, it appears on different positions on the screen. All right. So usually when it diffracts and then they end up at different positions on the screen, what we'll tell you is that violet will always be closest to the center and red is the furthest away. Okay. Why do we say that? You see, when you look at this screen right now, violet is over here. Violet is purple. Okay, it's closest towards the center. Red is furthest away from the center. Okay, why is it so? It's because Roy G. Beef, this one lambda decrease. So d sine theta equals to n lambda. So if I'm talking about d and n constant, sine theta proportional to lambda. So generally speaking, what we'll say here is that when lambda is decreasing, sine theta decreases. Therefore, theta decreases. This one will be closer to center. Closer to center line. But on the other hand, if your lambda increase, that means your sine theta increase, your theta increase, this one will be further from center line. Okay, that's the understanding here. That's why violet is closest to the center, red is the furthest away. Okay, now as for why the center maxima is always going to be white, it's because all the waves hit the same spot. The waves of different wavelength all hit exactly the same spot. The center line is where your angle of diffraction for all the different colors is 0. Okay, they don't diffract, they don't go and bend to another different direction. They're all just going to move straight. So because they all move straight and hit the same spot, the colors actually combine together to give you back white. Okay, that's why your center is always going to be white, because all the colors did not bend. They all move straight and coincide at exactly the same spot. Therefore, you get back white. All right. Okay, so the part why you would have different, why the colors will smear out, why certain colors will be closer towards the center, why certain colors will be further away from the center, that one I actually wrote here as the explanation, but I actually also wrote it inside the notes here. All right, so basically it's the same thing. All right, so red light has the longest wavelength in the visible light spectrum, so it will always appear at the greatest angle. Violet light would be the smallest wavelength, so it will always appear closest to the, it will always appear at the smallest angle, right? So this one, what I'll say here is this: red light, largest wavelength, it will appear at the greatest angle. That one is this one. Violet light, I did not say anything here. Violet light is actually the smallest wavelength. Its angle would be the smallest. So that one is for this. Okay, so let's just have a look at this question under page 12. Okay, then I think I'll give you guys a short break. Page 12, question 29. Let's have a short look at page 12, question 29. This is what I was just talking about. Page 12, question 29. Just look at that. Okay, we tell you white light consists of many wavelengths. The wavelength of red light R is approximately twice the wavelength of violet light V. White light is incident normally on diffraction grating. Several spectra can be seen. Which diagram shows the possible distributions of light in the first and second order spectra? Okay, so just by looking at this, you can actually do something like process of elimination here. Just now I mentioned specifically to you that the center must be white. Okay, if you look at this one, I mentioned specifically to you the center must be white. So you look at this question, there are two choices where the center is not white. You look at B, B is not white at the center. D is also not white at the center. It's actually having the rainbow spectrum. Okay, so the only possible choice of answer is either B or C. So which one now is actually going to be the correct one? Both are having white at the center. So the only thing that you can do now from here is that Roy G Biff, so this one I'm reproducing the same thing. Lambda decrease, d sine theta equals to n lambda, d and n constant would mean sine theta proportional to wavelength. Okay, so same thing as what I just wrote. Lambda small, sine theta small, angle small. Lambda big, sine theta big, theta big. This one is closest to center. This is furthest from center. Okay, so which colors would this belong to? If you have the biggest wavelength, giving you biggest angle, therefore furthest from the center, that one will be red light. Okay, so this one will be red. If you have smallest wavelength, giving you the smallest angle, you will be closest to the center. This one will be violet. So when you compare between A and C right now, the one that should be closest to the center must be violet. The one furthest from the center must be red for each order number. Okay, for each order number. So the answer is actually going to be C. Okay, answer is C. Right? You see, for first order, violet is closest to center, red is furthest. And then for second order, violet is again closest to center, red is furthest. So answer is C. Right? So this is the answer.